As always, let's begin by starting MCUXpresso and creating a new project. Again, I'm going to use the Quick Start panel in the wizard, and I need to identify the board that I want to create the project for. Here it is, the MCUXpresso 55S69 EVK board. This is the board I want to use. Next, we now configure the project. All I'm going to do today is give the project a simple name. I'm going to call it clocks. And this is everything that we need to do. So let's finish. And the project is created. MCUXpresso IDE will take us into the Project Explorer and open the new C source module, LPC55S69 clocks.c. And it's created the shell of a project for us. It's going to printf hello world. Let's change that to printf clocks. Okay, I select a project and I'm going to build it. And we can just confirm that the compiler can build this project. We get an ELF output file, suffix AXF, so we're good to go. Now we know that we want to use the clock out pin, and so we'll use the pin configuration tool to configure that pin. We'll open the pins tool. We saw how to do this in video number 2. So we're just opening the pins configuration tool. And here we are. A very simple thing we need to do now is to find the GPIO pin that we want to configure. Now we saw earlier on that this is port IO 0 and it's pin 16. So I've just typed it there and we can configure the pin. It's pin number 14 on the microcontroller. And we select the pin for routing, and I'm going to select the clock out functionality now. Green tick here, the pin's been routed, and in the routed pins we can see that pin 14 is routed to clock out. We're done. Now we need to update the code. So we use this button here, update code. We're going to update the code. These are the C source modules that are going to be changed. This is okay. Okay, and we're back into MCUXpresso editor, and the C source module that's just been created is up here in the boards group, and it's pinmux.c and pinmux.h. That's our clock out pin configuration. Next, we want to configure the clocks for the microcontroller. What I'm now going to do is use the clocks configuration tool. We can open that here. And we see a clock diagram. It's the clock tree for all of the microcontroller. It shows me the clock sources for the microcontroller. There's a free running internal 12 MHz clock and a free running high frequency 96 MHz internal clock. Of course, we can use an external crystal. So the crystal in and crystal out pins are down here, and this can be routed into the PLL to generate other clocks. And then we use these main clock multiplexers to select which particular clock we want. If I come to the overview, I can see 3 functional groups have been set up. It's a clock running from the free running internal 12 MHz oscillator. In the clock tree here, we see the free running 12 MHz oscillator outputting a clock through the multiplexer and out to the system clock. Alternatively, I can select the 96 MHz free running oscillator, and in this case we're using this clock source through the multiplexer, and we can see 96 MHz output. And then lastly, there's a functional group called PLL100. This particular functional group is going to configure the crystal to take a 16 MHz clock in and route that into the PLL0 to multiply it up to 100 MHz and select the 100 MHz clock to be output to the system clock. First of all, let's use the 12 megahertz clock tree. So I'm going to select functional group free running oscillator 12 megahertz. And now I need to enable the clock to the clock out pin. So let's find the clock out pin. That shows me the clock out here. And we can see that the clock out pin is currently inactive. It's inactive because it hasn't been connected to a clock. I'm going to select this multiplexer and select the main clock as the input. The main clock is routed through this clock divider, divide by 1, and it's going to output 12 megahertz onto the clock out pin. This main clock is the node up here, which is the output from the multiplexers. You can see in blue, free running oscillator is making the main clock. And that drives most of the system, including the system clock for the CPU and the system buses. As always, we're going to generate the code. So I'm using this functional group called boot clock free running oscillator 12 megahertz. So let's update the code for that. Again, it's prompting me to accept the changes it's going to make to the C source. And now we've configured the microcontroller to configure the 12 megahertz free running oscillator to be the main clock. In the main function, it calls this function init boot clocks. If we go look at that, F3 will take us over to the function, and what we can see is it's defaulting to using the free running oscillator 96 megahertz. That's not the functional group I want to use. I want to use functional group boot clock free running oscillator 12 megahertz. So I'm just going to copy that function and paste that into my main routine, and I am going to run that just here. Okay, we're going to initialize the free running oscillator 12 megahertz. Okay, that's all of our code. Let me save all of our source. I use the build wizard down here to build my project, and this time I'm going to download it in a debug session to the microcontroller. It's a new project, so of course MCUXpresso is going to do a probe discovery. I've got the LPC55S69 EVK connected through the debug port, so it finds the LPC link to. That's okay. Now it's looking for a core, and it will find both cores, core 0 and core 1, of course defaulting to core 0. Okay, we're going to flash up the microcontroller and sit here in main. Well, I'm just going to run over the code now. I'm just going to hit resume, F8, and my code is running. It came through all of this initialization code and now is running in this while loop. But if I turn to the oscilloscope, I can see a 12 megahertz clock output on the clock out pin. And this ability to monitor the internal clocks on a clock out pin is an essential technique for doing embedded designs. I always recommend that you actually measure the output from the internal clocks just to confirm you've got your microcontroller configured correctly. Well, let's try something else now. I'm going to stop my debug session and I'm going to return into the clocks configuration tool. Opening the clocks again, and this time I'm going to change from functional group free running oscillator 12 to the free running oscillator high frequency 96 megahertz functional group. Again, we can see the 96 megahertz frequency output here through the multiplexers and to the main clock and output to the system clock. Now I have changed functional group, and now I need to also set up the clock out again for this particular functional group. Again, we select the multiplexer. I'm going to select the main clock, and we're going to have a 96 megahertz output. I think that might be a bit high, so I'm going to divide that with the output divider by 96. This is going to make a 1 megahertz output signal. That's all the changes we need to make. So let's update the code, and return back to the editing environment. Now again, we need to change the boot clock. So I am now going to use the function boot clock free running oscillator high frequency 96. Let me copy that function, and we're going to call that function as the code runs. And now we're going to run the free running oscillator high frequency 96. Incidentally, we can look at the code that was generated. The clocks tool has written this code for us, and it configures the free running oscillator for 96 megahertz. Let me save my edits, build the project, and download it to the board. No need for probe discovery this time. We can just flash the microcontroller and let me run it. And in this case, if I turn to the oscilloscope, I can see a 1 megahertz output frequency on the clock out pin. That's the 96 megahertz from the high frequency free running internal oscillator divided by 96. Well, as a final test, let me stop the debug session, return to the clocks tool. Let me now change to the PLL settings. So I'm going to use functional group PLL 100 megahertz. I select that here, and in this functional group, the software is going to configure the clock in to 16 megahertz, and that's going to be routed down through the PLL to make a 100 megahertz signal for my main clock. The microcontroller will run from the PLL at 100 megahertz, and once again, down here with the clock out, I'm going to select the main clock. And again, 100 megahertz is a bit high, so I am going to divide by 10 to make a 10 megahertz output from the clock out pin. That's my changes made. Let me update the code again. Changes will be made to the software, and the function that I want to call this time is the PLL 100 megahertz function. So that's this one just here. And I'm going to change the configuration for the chip so that it runs from the 100 megahertz PLL. Let me save the code, I'll build it, download it to the board. Run my code. And if I look at the scope, I can see 100 megahertz divided by 10 and a 10 megahertz clock output on the clock out pin. Note that it's a very precise 10 megahertz because it originated from a crystal oscillator. Well, that's it. Let me stop the debug session. That will return me to the edit window. As always, I'm going to close the project, and that will complete today's experiment with the clocks tool. I just showed you how to change the clocking of the LPC55S69 microcontroller using the clocks tool in MCUXpresso IDE. You can do this. Let me know that it worked by leaving a comment below, and if you enjoy these videos, please subscribe to my channel, like the video, and share it with your friends. Thanks for watching, and see you next time when I'll investigate the Trust Zone Security extension for ARM v8M architecture. Bye.